Hey everyone, Morgan here. So reach for your calculators. We're going to be doing a little bit of math today. All right. We're on page 4 of the lecture outline dealing with reaction rates and kinetics. And I just want to remind you of something. Time. We said time was how long, and rate is how fast. Those words do not mean the same thing. Okay? And that's going to come up a lot in today's talk. So a reaction rate, R, is equal to the change in concentration over the change in time, which is C2 minus C1 over T2 minus T1. And remember, I'm trying to use these scripty little t's for time and a capital T for temperature. So I'm going to draw a graph that represents an interesting reaction. 2N2O5 breaks down into 2NO2 and O2. Okay? Now, when that happens, we can actually plot time versus concentrations measured in molarity. Now, the N2O5 concentration comes down and looks something like that. So over time, its concentration is going to decrease because it's a reactant and it's being used up. Now we could find the reaction rate for this at any given time by measuring the slope of what is called the tangent line. You learned about those in geometry. Okay? Now we also are going to have two other lines. And this is the concentration of NO2, and this is the concentration of O2. Now you notice that since they're products, both of the lines go up, and eventually they settle out the same way the N2O5 steadies out. But the NO2 concentration is twice as high as the O2 concentration. Why is that? It's because we look at the mole ratio. All right? You have 2 NO2s for every 1 O2. Twice as many moles, which means twice as high a concentration. And at any given point, R equals C2 minus C1 over T2 minus T1. Okay? That's important to know. Now, there's a mole ratio here. 2 N2O5 gives us, 4 NO2. Hold on. I had the wrong thing up here. That's not a 2, that's a 4. I am so sorry about that. 2 times 2 is 4, so 4 nitrogens. 2 times 4 is 8, plus 2 is 10. There we go. I'm so sorry. So this will be 4 times higher than that. Okay? Now, here, what we say is that the mole ratio is 2 to 4 to compare N2O5 and NO2, and 2 to 1 to compare N2O5 and O2. And we did a whole lot of that back in, the stoichiometry unit. And we're going to kind of look at the same thing with it today. So let's move on. Page 5. Okay. So, the concentration of a substance in a reaction changes from 2.0 molar to 1.0 molar in 20 minutes. Express this rate of the reaction in molar per minute. R equals change in C over change in T, which equals 1.0 molar is the final, 2.0 molar is the initial, 20 minutes minus 0, okay? So, this equals negative 0.050 molar. Now, that is allowed. I'll rewrite that a little clearer. Negative 0.050 molar. That's allowed to have a negative number because it's going down. Okay? The reaction rate is decreasing. It's not as fast anymore. Now, for the next one here, let's compare a couple of rates, okay? So we're starting out if the change in the oxygen concentration is 1.0 molar per second for O2, because it's the oxygen concentration, what is the reaction rate in terms of dinitrogen pentoxide, which is right here? Okay, so what we do is we say in this equation, 1 mole of O2 gives us 2 moles, N2O5, okay, and this equals 2.0 molar per second, N2O5. Now, we could throw a negative sign in to say that this one is going down while that one is going up, okay? Or we could also use words like, increasing, decreasing, all right? The different ways to express the fact that it's a reactant rather than a product. Okay, so that's a little bit of the math stuff, and you're going to be doing a bunch of graphing in your next homework dealing with this. Okay, that's Morgan, finishing off this video.